Okay. You can do the exponential of a matrix, but that's really difficult to do if the matrix isn't diagonal. If the matrix is diagonal, then, well, the fundamental idea is if you have a diagonal matrix and take the mth power of that diagonal matrix, you just get the mth power of all the elements in the diagonal and zeros everywhere off the diagonal. Now, since that's the case, you can do a sum of nth powers, whatever, meaning you can do the Taylor expansion of any function, because the Taylor expansion is just an expansion in powers of your variable. So, number one, you should absolutely be able to quickly write down the Taylor series for e to the x sine x cosine x. Okay, so I should make a note there. You should be able to quickly write down the Taylor series for e to the x sine x cosine x. And there are other functions, but those are the main ones that are going to arise in solving systems of differential equations. You can then replace x by a diagonal matrix, because of course we know that these expansions are going to be in terms of powers of x. And you can do powers of exponential, of diagonal matrices. Okay. Since you can do this, you can easily then prove that e to the diagonal matrix times t is just the matrix that you get if you do e to the lambda 1t, e to the lambda 2t, all the way down to e to the lambda nt. Okay, it's because the Taylor series expansion of this is going to involve all the powers of this matrix. And for every element, for every diagonal element, you're going to have all the powers you need to build up e to the lambda 1t. And same for any diagonal element. And you can easily then prove the same for the cosine or the sine. The cosine of a diagonal matrix times t is what you get, is the diagonal matrix you get when you have the cosine of lambda 1 through lambda nt on the diagonal. Okay. And again, it's not difficult to understand that if you have a basic understanding of Taylor series. And remember that we did that in quite a bit of detail, at least for the exponential function, in class. I also mentioned that, now that you know this, well, never mind, I'm not going to say that now. Okay, makes sense? Hopefully. Now this is, if you know all this and know it really securely and can do it reliably, and your whole goal is just to pass this course, you can get by without knowing this. But this isn't that hard to know, and since you're, if you don't understand this, chances are you're not going to be as secure as you need to be on this to be able to do it with very few errors, very few point penalties. The best you could do just knowing this and the analogous stuff that we'll see with the Laplace transform would be a C. Okay, if you want to make an A or B, you've got to be able to do this to whatever extent is necessary for that grade. And the applications of this. And of course, you have to know how to diagonalize a matrix with the similarity transform. So I just mentioned diagonalization. I assume everybody knows that you, to diagonalize a matrix, you get your eigenvalues. You use those to get your eigenvectors, and you form the square matrix whose columns are the eigenvectors. That's your T matrix, and you do the similarity transformation involving the T matrix. So I'm just saying, you know, that's like T, A, T inverse. Okay? And actually, I think it's T inverse A T. I never do that right, and I have to think every time I do it, and I don't mind that. If that's not right, then it's T A T inverse. I don't want to get into that explanation right now. What you're doing is you're transforming your system to the basis of your eigenvectors, and in that basis your system is diagonal, and then you're pulling it back to the original system. So you need to basically understand that, because just understanding that process and what it means in terms of the basis of the two different systems is your key to always being able to do this without having to go through a lot of gyrations. And you just draw your commutative diagram. You know, you got one thing here, one thing here, you got your A matrix here, you got your diagonal matrix here, and you pull the A matrix up and do the diagonal, push it back down. And one of these is T and one of these is T inverse. Okay? And you have to understand how that is, or at least remember how it is. I understand how it is, but I don't want to think it through right now. Okay? Just finished the last day of classes. I'm pretty well not wanting to stick my neck out on that. I think I know which way it is. And I can easily reason it out. I'm not going to take the time.